I'm Eric the Electron, and this is my dilemma. I really want to get to that photon so I can get to an excited state, but the rules of classical mechanics forbid me from getting through this barrier because it has a higher energy level than I do. Is there any other way that I can get to the other side of the barrier while still abiding by the laws of physics?
So first thing you have to understand is that an electron, you exist more like a probability cloud than a particle. So you expand rapidly, your probability of being in each region decreases. So probability of being in region 1 is greater than your probability in region 2, and which is greater than in region 3, and so on.
So what you're saying is that I'm not actually just a particle, but I'm a cloud of just probable chances of being anywhere in that cloud?
No, you're still a particle. It's just that it's easier to describe you as a cloud because of Heisenberg's uncertainty principle. Say you had a barrier here, and you're somewhere in this region 1. There's still probability that you'll be over here in this region. So quantum mechanics states that even though this barrier has a higher energy level than you do, there's still a chance that you'll end up on the other side because of electron tunneling. And that the only difference is that the energy level will be decreased because of this barrier.
So what you're saying is that if I come at this barrier, then there's a probable chance that I can appear on the other side? Alright, let's try it. What happened?
Because the potential energy of the barrier was higher than your energy, that difference dictates the likelihood of you appearing on the other side of the barrier. And so if you increase the energy and thereby decreasing the difference, you'll increase the probability of appearing on the other side of the barrier.
So I just need more energy to have a higher chance? Alright, I'll get a running start. More energy?
More energy.
We did it! Alright, now I'm just gonna go get my photon. What happened? I have a higher energy level than that low energy barrier, but I was still reflected onto the side that I came from.
So that's basically what's happening. Here's the barrier. Here you are. And here indicates the potential energy of the barrier. But even though your energy is greater than the potential energy, obviously, there's still a chance that you get reflected back. One way of thinking this is consider this eraser. Your potential energy depends on its location. So if I drop this eraser here, this velocity will be greater if I drop it here. The difference is, in classical mechanics, your energy, regardless of your energy, if you try to go over a barrier, you always go over, but in quantum mechanics, there's a slight chance that you'll come back.
Okay, so I actually have a pretty high probability of making it over this barrier. So I just need to realistically try enough times and I should make it over pretty quickly. Let's do it. All right, I made it over the low energy barrier. Time to get my photon. I'm so excited.
Does that make sense?
Okay, I guess that all makes sense. But Professor, I have one last question for you. What's that over there? What's the big deal?
So basically what happened was, this was your incident wave, this was your transmitted wave, but a part of you still got reflected. And its energy is much less than the incident and then transmitted, because the energy of the incident is equal to the energy of the reflected plus the energy of the transmitted.
All right, so let's think of some real life applications. So one of the more commonly used examples that we use for quantum tunneling is alpha particle decay. And so one way to describe this is, let's say that we have a really big nucleus, something along the lines of the atom of uranium. So in the atom, we're going to have a whole lot of protons and a whole lot of neutrons. And what those are all going to do is they're going to make a big shell. So we've got about half protons, half neutrons. The protons are all positively charged and the neutrons have no charge at all. And so what those all do is they make a big shell. And the forces that are on that shell is the Coulomb force and the nuclear force. So those are the two forces that we care about. And the Coulomb force is going to be the repellent force. And the reason that we have that is because since we have all these protons and there's no electrons in there, it's just positively charged, all those protons are going to be pushing against each other. They're going to be repelling each other because of the electromagnetic force that they hold. Protons are repellent. It's just a bunch of positive charges. And then the nuclear force is what happens when we have a bunch of subatomic particles that are all really, really close to each other. They have a really strong attraction, and that's what's called the strong force. And so that's the effect of the nuclear force. And so the combination of those two is going to be what holds the nucleus together. And so basically, the bigger the particle that we have, so this is why we use something like uranium, the more unstable it's going to be, just because there's so many particles. So something that's going to be a lot more stable is going to be something like the lithium. Our lithium nucleus is going to be a lot more stable than our uranium nucleus. So what we care about is what's at the very center of that uranium nucleus, which is our alpha particle. And our alpha particle consists of 2 protons and 2 neutrons. 1, 2, 3, 4. And so basically what alpha particle decay is that alpha particle wants to shoot outside and be emitted from that nucleus. And what that looks like is we actually draw graphs to represent the potential energy of that nucleus to show how easy it is for that alpha particle to decay. And so those graphs look a little something like this. So this is what a graph for the potential energy for uranium nucleus would look like. And we've got our alpha particle that's just sitting in this little peak right here. And then for our lithium, it's going to look a little something like this. Again, with the alpha particle sitting at the bottom, just like that. Now, you can obviously tell that there's a big difference between these two graphs. and that's that one of these is a lot more stable than the other. And so the way that we can tell how stable this is how long it would take for this to quantum tunnel. So just like we talked about before, where the electron needs to tunnel through the barrier, even though it has a lower energy than the potential energy barrier. So right here, this alpha particle, even though you can hardly tell, is actually at a lower energy than it is at the top of the barrier. So if we drew a graph right here, here's the energy of the alpha particle, and here's the energy level of the top of that barrier. And it's actually a little bit less, so what it's going to have to do is it's going to have to quantum tunnel. It's going to tunnel right outside there. And since that gap is so small, it's going to be a lot easier for that alpha particle to decay and tunnel outside and be emitted from that nucleus than it is for something like lithium, where as you can see, it has to travel a lot farther to get outside, because that difference is so much farther. Now, the question that I have for you is, I'm actually going to ask you a question about this, and that is, which one of these is going to actually emit more energy when it goes through alpha particle decay? Is that going to be our uranium nucleus, or is it going to be our lithium nucleus? I'll say that again. Which of these is going to actually emit more energy? All right, I'm assuming that you picked uranium because you're all smart, and the reason for that being is that if we look at this just like a classical mechanics potential energy graph, if that alpha particle gets emitted on the outside and it goes right here, it's going to slide all the way down this ramp, just like if it were to slide down a skateboard ramp and shoot down. Now that's a long distance for that to slide, so it's going to actually gain a lot of energy, and that's all the energy that's emitted from that reaction. Whereas this one, once it goes outside, it's just going to slide down this little ramp right there, which is a lot less for it to travel, and that's why it's going to actually emit so much less energy. Now, the time that it takes for that alpha particle to travel through this little barrier could be a millionth of a second, whereas the time it takes for it to travel outside here could take hundreds, thousands, millions of years. So that's why this uranium is actually so much more unstable than this lithium nucleus, even though this one's going to actually emit so much more energy. And so that's the main premise of alpha particle decay, and that's why we use quantum tunneling in normal physics today.